Okay, now we will talk about, in this video, we'll talk about Hartnell governor. So you have seen this governor in your practical, and you see that here in this governor, we have this spring here. Okay, then we have bell crank lever. This is called the bell crank lever. Okay, and then we have, these are the masses, right? And you can see that, just a moment. Yeah, so mass is at this position. What happens when you start rotating this, mass moves away from this, then the bell crank lever takes a shape like this. Yes, the sleeve will be lifted. Fine. Now when the mass speed is reduced, masses will move towards each other, and the sleeve bell crank lever takes a shape like this. Okay, so one thing, the distance of the mass from the axis of rotation is the radius. Okay, radius. So when the speed is less, okay, let's start write as minimum speed as omega 1 and maximum speed as omega 2. Okay, so in this case, for minimum speed, radius will be r1. Okay, and then it will be here. Here, bell crank lever, masses will move towards each other, and when the speed is omega 2, mass will move away. So the radius, let's term it as r2. Okay, so we will write it like this here. This is the first case when the mass is moving towards each other. See, mass if moves in this direction, so this is how it will take a when the sleeve is going to move down, so this will come closer to the axis. So this is the point. Okay, this is the mass. You can see mg is the weight of this. Okay, yes, we'll have, so r1 is the radial distance from the axis of the rotation. So it will have a centrifugal force of m1 m, small m, r1 is the distance, and omega 1 is the speed. So m r1 omega 1 square is your centrifugal force outwards. Okay, and here you can see we have mg, that is the mass on the sleeve, into g, that is the weight. Okay, plus the frictional force we previously had in Porta governor, mg plus f by 2. Okay, but in this case we have a spring also. Okay, so at the minimum speed, spring will exert some force, that is called fs1, we call. Okay, fs1. And when we have the maximum speed, with the spring gets compressed at maximum speed, mass is moving away. So what will happen to this sleeve? This sleeve is will take a shape like this. Then sorry, the bell crank lever will take a shape like this, and the sleeve will be lifted. Then the uh, spring will put some different amount of force that we will term as fs2. Okay, so this is the second case when the bell crank lever is in this position, and here you see mass is here now. Okay, and the mass is mg, radius will be more now. Okay, because this is r2. Okay, we'll just term it as r2. Speed is different, omega 2, so the centrifugal force is m r2 omega 2 square. This is mg, and since the friction sorry, spring force is different now, we'll just write it as fs2. So mg and f are general values. Okay, we'll just take them as constant. Okay, they are not changing in this case. We'll just take it like that, because this position is a2 is not exactly you see, sorry, okay, sorry, what I wanted to tell you is, this point, you see, this will not remain at the same point. This is the minimum point. Okay, when the sleeve gets lifted, no, this will also move. This point will move. I mean, this point means this point here, the pivot point will go up, and then it will take a shape like this. And when it comes down, then this is the shape of the bell crank lever, and this point here will move to this position. Okay, so obviously the vertical distances also will change. So from here to here, this distance is a1. Okay, a1, and next it will actually, in this case, will reduce a2. Okay, so this is the distance from for the mass actually. So we'll have to take care of that change also. So now in generalized condition, this capital M mg, this will remain the same, and the frictional force is the same. Only changes in the spring force. When we are going down, spring will not exert much amount of force. So we have taken it as Fs1. So when you are moving up, spring will exert some force, that is Fs2. Okay. So two conditions we have actually taken. So when the speed increases, balls move apart. So these are the things we have written, and please go through them. Okay. Now we have seen that the general centrifugal force is given by mr omega square, and Fs is spring force. So we have two here centrifugal forces. M r1 omega 1 square, we have seen it here. Okay. And another centrifugal force is mr2 omega 2 square. This is the second one. Okay, now what we'll do now, we will take moment about this point for each of the case. Okay, for first and second case. So what happens if we take the moment about A in this case? See, this will create a what? Anti-clockwise moment, the centrifugal force about A. This will create a clockwise moment about A, and this force will also create a clockwise moment about A. Okay, so we'll write this moment, anti-clockwise moment, in the left hand side, and these other two moments in the right hand side. Okay, we will have it like this. mr1 omega 1 square is the force. What is the distance between A and this force is A1. Okay, so multiplying this with A1 equal to this whole force multiplied by the distance between A and this force is B2. Okay, so the whole force multiplied by, oh sorry, we are talking about the first one, sorry, B1. So this whole force multiplied by B1. Okay, so what remains? Mg. So mg multiplied by the distance between the point A and the force is C1. So we write it as C1 mg square. Similarly, for the second case, mr2 omega 2 square A2 is the distance here, you can see between A and this force. A2 is the distance between this force and A point is distance is B2, so we have multiplied here B2, and between mg and this point A is distance is C2, so we multiplied C2. Okay, when this angle theta, we have actually seen two angles, theta 1, theta 2. When these angles are very small, okay, then we can take A1 equal to A2, B1 equal to B2, C1 equal to C2. So what we can just simplify, we can just simply write here this one, this we have combinedly written this as F1. Okay, let's write this F1. So F1 into A. So F1 into A. Okay, A, because we have just equated A1 and A2 to A, B1 and B2 to B, and C1 and C2. See, these are zero because you see, because if the variations are not there, B1 and B2 are same, A1 and A2 are same, then these will not go here and there. Since theta is very small, we just think that C1 is very small, C2 is very small, so we just consider them as zero. Okay, so these two terms will not come into picture. So we will have F1A equal to half of this thing. We, instead of B1 we write B, and this is F2. This is different. Okay, because this is another centrifugal force. F2A equal to half mg Fs2, this one. Okay. Now we take there, we subtract one equation, this 1 minus 2. Sorry, 2 minus 1. So this will be F2 minus F1, second centrifugal force minus first centrifugal force into A, equal to this mg gets cancelled out. If we subtract it, F gets cancelled out. Okay, and then we'll have only the spring forces, Fs2 minus Fs1. So this is, we can find out a difference between the spring forces by rearranging it. Okay, now if S is the stiffness, sometimes we write K also, spring constant. Okay, so stiffness of the spring is given by S, suppose, and H is the movement, H1 suppose is the movement of the sleeve. Suppose this spring has a spring constant of S, and H1 is the movement of the sleeve, H1. Okay, so we can write it like this. Here you can see, generally what happens, spring force is equal to what? Suppose the in most general case, this is the spring. Okay, so the if the spring is given a force and the distance moved is x, suppose, then this force F and the stiffness is S, suppose, then force F is equal to, okay, equal to S into this X, okay, the movement one. So here, what we can, here the spring constant is S and the distance moved is H1. So we can write this as S into H1, okay, distance moved is H1. So we have written this as H1S, okay. This is the difference between the spring forces. So the net spring force is equal to the distance moved into spring constant, okay. So we can just put it here, h1 into S. So h1 into S is equal to this, and we can find out S from here by just rearranging a little bit more. Theta equal to arc length by radius, we just find it from this diagram here, okay. So we can actually get this S spring constant from here, okay. Finally, by rearranging it, we have spring constant S equal to 2 into A by B whole square into F2 minus F1 by R2 minus R1. Now let's just familiarize with this term. What is A? A is the distance from here to here, okay. So what you have to do is, you just have to, what you do, you draw one of this figure, okay. Then you one of these, either this one or this one, then you will know this is A, okay, and this is B, right. So actually this is B, okay, and this is A. You have to be familiar with these things, okay. In your practical, you have seen these two arm lengths. So this is A and this is B, okay. And then what else? A and B are known now. So F2 and F1. F1 is the minimum centrifugal force, F2 is the maximum centrifugal force, okay. At a slower speed, we'll have a centrifugal force which is minimum, we consider, and at the higher speed, centrifugal force is more, so we'll consider that as higher frictional forces. And then R1 is there and R2 is there. What is R1? R1 is the minimum radius, okay, of rotation for the masses, and R2 is the maximum radius of rotation for the masses, okay. So if you are given with all this, you can find out the spring constant, right? And using these equations, you can find out the spring forces if required, okay, and if frictional forces also if you want. So spring forces can be found using this, okay, if F1, F2, these are known. All right, so let's look at the problem here. So in a Hartnell governor, the extreme radii of rotation of the balls are 40 mm and 60 mm. That means, let's look at this extreme radii. So radius of rotation of the balls are given. So at this position, this is 40 mm. Okay, 40 is less than 60. So this one, the second position is here. Okay, so this one is 60 mm given. Extreme radii of rotation. Okay, for this one is 40, this is 60. This is given to you, okay, in the question. Next is corresponding speeds are 210 and 230. Obviously, you see, at a lesser RPM, your balls are more closer to each other. So that's why radius is 40 mm. At a higher speed of 230 RPM, your balls will move apart. They will go away from each other. So that's why their radius of rotation will increase to 60 mm. Understood? So you are given with what? N1 and N2, you can say. So we can find out omega 1 from this. Omega 1 is the slower speed. Omega 2 is the higher speed. From here you can find out. This will be R1, this will be R2. Yes. The mass of each ball is 3 kg. So M is 3 kg. Small m is 3 kg given. So length of the ball and the sleeve arms are equal. That means A1 equal to A2, A1 equal to A2, and B1 equal to B2. You can take them as A and B only. Okay. Oh, sorry. I'm sorry. The length of, what is that? The length of, what is it? The length of the ball and sleeve arms are equal. Oh, then actually we can say that ball and sleeve arm. Okay. This is ball arm. This is sleeve arm. Okay. So A equal to B. That is given in the question. So ball arm, sleeve arm are equal. Both lengths are equal. So A equal to B. So we have further simplified the question. Determine the initial compression and the constant of central spring. That means Compression, initial compression will be actually H1, and the spring constant they are asking, spring constant. Okay, so let's just simply solve it using this. So in the question, you are given with A equal to B, so this term will not be there. F2 and F1 you can find out because M is known, R1 is known, R2 is known, omega 1 and omega 2 you can find out. R1, R2 is given in the question. So let's find out the stiffness. How to find? First you find omega 1 and omega 2. Okay, N1 first speed is given 210. So omega equal to 2 pi n by 60. So we'll put n value 210. So 2 pi into 210 by 60. This is 22 radian per second. Similarly, for this omega 2, 2 pi n by 60. So 2 pi into n is 230, 230 divided by 60. So we have got omega 1 and omega 2 here, 22 and 23.04. Okay, fine. So we can find out the centrifugal force now. First centrifugal force, that is the minimum one, m r omega 1, m r1 omega 1 square. Because the radius is different, in both cases we'll have two different centrifugal forces. So mass is 3 kg given, r is 40 mm, 40 mm converted to meter. So 40 divided by 1000, that is 0.04, and omega 1 we have got 22. Calculate f1. Similarly, calculate f2. M is 3 kg given, r2 is 60 mm, so that is 0.06 meter multiplied by omega is 23.04. Put it here, you will get this f2. Okay, now just simply put in the formula to get the spring constant. How will you get? 2 a and b are equal, so this is 1. F2 value is this, f1 value is this, r1 and r2 are given 60 and 40 mm, so 0.06, 0.04. So you have got the spring constant 3750 Newton per meter, converted to Newton per millimeter. So this is per millimeter, means you have to divide it by 1000. So 3.75 Newton per millimeter. Okay, so it got the spring constant. What they are asking is sleeve lift. Okay, also initial compression, you can say initial compression. So oh, I'm sorry, initial compression means the compression force they are asking, sorry, not the sleeve lift. They will say that this is the movement. So initial compression is fs1. Okay, spring constant, spring force actually, f initial compression of the spring, that is f first at the beginning we compress it here. Okay, I mean the spring will be compressed here f2 by force of fs1, and when you move further the force will be fs2. Okay, fs2 in this case. So what happens here? So initial compression is fs1, initial compression force, and final compression force is fs2. So you have to find out fs1. So you just take help of this equation. Okay, where is it? This one. Okay, so f1 equal to half mz. Let's write down the equation here. F1 equal to half mz fs1 plus f. This term will not be there because we take we take a and b equal to, here actually b is multiplied, huh? Half mz fs1 plus f, both b, actually b is missed here because in the equation it is there, this b is there, b. So plus this we have taken c1 and c2 equal to a very negligible value, so we have taken this 0, this term will not come, but we have written it here, so no problem. So we have to initially c is 0, that's why this is not there. Okay. And one more thing, mass of sleeve we have assumed it to 0 because this is not given in the question, not given in the question. So if it is not given the question, you can suitably neglect, or if you want to take any value, assume any value, you can take it. Okay, so like that you solve in the question in your exam. So here this is not given, so we don't take this thing. Okay, now frictional force is in this case again frictional force is also not given. Okay, so you can neglect frictional force also. Okay, this mass and this are negligible. Okay, so or one more thing you can say, this is 0 because it's an initial movement, so from initial to final there will be a movement of the sleeve, then only there will be friction. Okay, so we have to consider dynamic friction in this case, not the static friction. So that friction at the initial point, we just think that friction is 0, then it will increase to some value. So we have since the value is not given, no, you have to take it as 0. Like the previous problem, we have taken it as 0. So here capital M is 0, friction is 0. So we are left with F1 A equal to half mg fs1. Mg we have taken this 0. A and B both are equal, so we can cancel each other. So F1 is equal to half of S1. Fs1 will remain. So F1 is equal to 3 into 0.04 to 22 square. It is 58.1 Newton. So 58.1. This is actually 58.1. This is point equal to half Fs1. So Fs1 you can find out from this 58.1 into 2. That is 116. So initial compression. Okay, sorry about, again I have made a mistake. The actually compression means the distance only. Okay, so Fs1. I'm sorry for all these confusion created. So simply I want to tell you that sorry, this H1, yes. So from this formula, they are asking only H1 only, initial compression. So initial compression means the distance. So this Fs1 divided by the spring constant will give you H1. So initial compression, this is H1 will be equal to Fs1, this force divided by is 3.75. This is S. Okay, using this relation. What is the relation? This relation. Okay. So by the way, here the difference has been taken, but at the initial point also we can take it like this. Initial compression. Fs1 is equal to initial compression or the distance into spring constant. So we have found out the initial compression using this. Okay, so we'll conclude the Hartnell governor here. The remaining problem you can see yourself. Okay, here this problem is about when the arms are not equal. Okay, and we have taken actually we have our values of the capital M and then F. Everything is given in this question. Okay, so this is a longer question. We'll discuss in the next video. Okay, so thank you.